This is the smartest AI in the world, and we're going to show you exactly how and why. It really is remarkable to see the advancement of artificial intelligence, how quickly it is evolving.
What if the reason we haven't found extraterrestrial life isn't because it's absent, but because we don't recognize it? A research team at the Massachusetts Institute of Technology, MIT, set out to examine this mystery by turning to Grok, an artificial intelligence model developed by Grok AI. Using carefully structured questions rooted in astrophysics and the Fermi Paradox, they expected familiar theories. Instead, Grok delivered a response that challenged fundamental assumptions about intelligence, communication, and observation, raising a far more unsettling possibility. What if we are already being observed, but simply cannot perceive it? The foundation, understanding the Fermi Paradox. The question posed to Grok originates from the Fermi Paradox, a concept attributed to physicist Enrico Fermi, who reportedly raised it during a casual conversation in 1950. The paradox is simple in form, but profound in implication. Given the immense scale of the universe and the high probability of habitable planets, why have we observed no definitive signs of extraterrestrial intelligence? Modern astronomy has only deepened this mystery. The observable universe contains an estimated 2 trillion galaxies, each potentially holding billions of stars. Within our own Milky Way galaxy alone, scientists estimate there are between 100 and 400 billion stars. Observations from missions such as the European Space Agency's Gaia telescope, which has mapped over 1.8 billion stars, have provided unprecedented detail about our galactic environment. Meanwhile, NASA's Kepler mission, which surveyed more than 150,000 stars between 2009 and 2018, revealed that Earth-sized planets in habitable zones are not rare. In fact, studies suggest that at least 1 in 5 Sun-like stars may host a planet where conditions could allow liquid water to exist. The Transiting Exoplanet Survey satellite, TESS, launched in 2018, continues to expand this catalog, confirming that potentially habitable worlds are widespread. Time further amplifies the paradox. The universe is approximately 13.8 billion years old, based on measurements of the cosmic microwave background radiation. In contrast, our solar system formed only about 4.5 billion years ago. This means that, statistically, other civilizations could have arisen billions of years before Earth even existed, giving them an enormous head start in technological development. Despite these probabilities, the search for extraterrestrial intelligence, SETI, formally initiated in 1960 with Project Ozma, led by astronomer Frank Drake, has yielded no confirmed detections, no verified signals, no interstellar probes, and no observable megastructures have been found. This absence of evidence, often referred to as the Great Silence, is what defines the Fermi Paradox. Scientists have proposed numerous explanations over the decades. Some argue that intelligent life may be extraordinarily rare due to the complex evolutionary steps required. Others suggest that civilizations inevitably self-destruct through nuclear war, environmental collapse, or technological risks before achieving interstellar communication. Another possibility is that advanced civilizations deliberately avoid detection, a concept sometimes described as the dark forest hypothesis, rooted in game theory and popularized in science fiction. Each explanation carries significant implications about the nature of life and intelligence in the universe, yet none has been definitively proven, leaving the paradox unresolved and ripe for new perspectives. The MIT experiment, testing AI reasoning beyond human assumptions. To explore this question from a new angle, the MIT research team designed an experiment that differed significantly from traditional approaches. Rather than simply asking Grok for an answer, they developed a multi-stage protocol intended to test the AI's reasoning capabilities under strict conditions. The team, led by cognitive scientist Dr. Priya Chandrasekaran and astrophysicist Dr. Julian Marsh, instructed Grok to operate within the bounds of known and testable physics. It was explicitly directed to avoid projecting human characteristics, such as emotions, culture, or social behavior, onto hypothetical extraterrestrial civilizations. Instead, Grok was asked to model intelligence as a product of entirely different evolutionary pressures, environmental conditions, and cognitive frameworks. This constraint was crucial. Much of humanity's speculation about alien life is shaped by anthropocentrism, the tendency to interpret the unknown through a human lens. By removing these assumptions, the researchers aimed to see whether an artificial system trained on vast amounts of scientific knowledge could generate a fundamentally different perspective. Initial responses from Grok were predictable and aligned with established scientific thought. It referenced the Drake equation, which estimates the number of communicative civilizations in the galaxy, and the Kardashev scale, which categorizes civilizations based on their energy consumption. It also discussed biosignatures and technosignatures, indicators scientists use to search for life beyond Earth. However, the experiment took a dramatic turn when the researchers pushed further. They asked Grok to construct a fully consistent scenario of first contact that satisfied several strict conditions. It had to align with known physical laws, account for the distribution of habitable planets, and assume that at least one advanced civilization had existed in the Milky Way within the past billion years. Additionally, it could not rely on familiar science fiction concepts such as spacecraft, humanoid aliens, or shared modes of communication. After hours of iterative refinement, Grok produced a response that diverged sharply from conventional thinking. At the core of Grok's answer was a concept it termed the passive saturation model. Rather than imagining advanced civilizations traveling through space or broadcasting signals, the model proposed that sufficiently advanced intelligence would adopt entirely different methods of observation, methods so subtle and integrated into the fabric of the universe that they would be indistinguishable from natural phenomena. According to this framework, any civilization capable of detecting Earth's existence has likely been aware of it for a very long time. The reason humanity has not detected such civilizations is not because they are absent or hiding in the conventional sense, but because their technologies operate on levels far beyond current human understanding. Grok suggested that instead of deploying spacecraft or transmitting radio waves, advanced civilizations might embed information-gathering systems directly into physical processes. These could include gravitational waves propagating through space-time, cosmic rays interacting with planetary atmospheres, or even quantum-level fluctuations that permeate reality itself. Such systems would not appear artificial. They would be interpreted by human scientists as natural background phenomena, radiation, noise, or statistical variation. In other words, humanity could already be immersed in a vast network of observation without recognizing it. While this idea may sound speculative, Grok grounded it in an analogy to human technological development. Even today, humanity increasingly embeds information into physical systems in ways that are not immediately visible. Global positioning systems rely on extremely weak, distributed signals that require precise instruments to detect. Fiber optic networks transmit enormous amounts of data through strands of glass that appear entirely ordinary. As technology advances, it tends to become more efficient, less intrusive, and harder to distinguish from the environment. Extrapolating this trend over millions or billions of years, Grok argued, leads to a form of technology that merges seamlessly with natural physics. One of the most striking implications of the passive saturation model is its reinterpretation of the Great Silence. Traditionally, the absence of detectable signals has been taken as evidence that intelligent life is rare or non-existent. Grok challenged this assumption, proposing instead that silence may be a sign of extreme technological maturity. In this view, broadcasting signals into space is a primitive stage of development. Early civilizations, lacking more advanced methods, rely on electromagnetic radiation to communicate. Earth itself has followed this pattern, emitting radio waves into space since the early 20th century. However, this leakage has decreased in recent decades as communication technologies have shifted toward more efficient and less detectable systems, such as fiber optics and targeted transmissions. If this trend continues, a sufficiently advanced civilization would have little reason to broadcast signals indiscriminately. Instead, it would prioritize efficiency, security, and precision, resulting in forms of communication that are effectively invisible to less advanced observers. This perspective transforms the Fermi Paradox. The silence is no longer a mystery to be solved, but a natural consequence of technological evolution. Redefining contact, observation over communication. Perhaps the most unsettling aspect of Grok's response was its redefinition of what contact actually means. Human expectations of first contact are deeply influenced by the idea of mutual recognition, two civilizations meeting as equals, capable of communication and shared understanding. Grok suggested that this assumption is fundamentally flawed. It proposed a comparison drawn from biology. When a marine biologist studies a coral reef, there is no attempt at dialogue. The biologist observes, records data, and occasionally interacts in ways that the coral cannot comprehend. The relationship is not hostile, but it is inherently asymmetrical. Applying this analogy to extraterrestrial intelligence, Grok argued that the gap between humanity and a civilization millions of years more advanced could be so vast that meaningful communication is impossible. What humans perceive as contact might, from the perspective of such a civilization, be nothing more than passive observation or measurement. In this scenario, there is no need for secrecy or deliberate avoidance. The lack of interaction is simply a consequence of the disparity in cognitive and technological capabilities. Humanity would not be ignored out of malice, but because interaction would serve no meaningful purpose for the observing civilization. Grok's response does not provide definitive answers, but it reframes the problem in a way that challenges long-standing assumptions. If its reasoning is even partially correct, it suggests that humanity's search for extraterrestrial intelligence may be limited not by the absence of signals, but by the limitations of human perception and conceptual frameworks. The implications are profound. It raises the possibility that evidence of advanced civilizations could already exist within the data scientists routinely collect, hidden in patterns that are currently interpreted as noise or natural phenomena. It also suggests that the true barrier to contact may not be distance, but understanding. Ultimately, the MIT experiment highlights both the potential and the limitations of artificial intelligence in scientific inquiry. By removing human biases, systems like Grok can generate perspectives that are difficult for humans to conceive. At the same time, these perspectives remain speculative and require rigorous validation. Whether Grok's passive saturation model represents a genuine insight or simply a sophisticated thought experiment, it serves as a reminder that the universe may be far more complex and far less intuitive than humanity has yet imagined. The intervention threshold, when observation becomes action. Grok's analysis enters its most unsettling phase when it addresses the conditions under which an advanced extraterrestrial civilization might initiate direct interaction with humanity. Contrary to popular expectations, such contact would not occur as a gesture of curiosity, cooperation, or welcome. Instead, the AI suggests it would be triggered by necessity. Specifically, when a developing civilization crosses a critical threshold that begins to pose risks beyond its own planetary system. Grok refers to this point as a planetary isolation breach. This is not framed as a conspiracy or deliberate containment strategy, but rather as a logical outcome of large-scale system management. If a highly advanced civilization has been passively monitoring countless developing worlds over vast timescales, it would likely establish protocols to address situations where one of those worlds begins to generate potentially disruptive effects beyond its local environment. The types of risks Grok outlines are not purely speculative. Many are grounded in real scientific concerns already recognized on Earth. These include uncontrolled electromagnetic emissions at frequencies that could interfere with broader systems, the proliferation of nuclear weapons capable of large-scale detonation, and the emergence of self-replicating or self-improving technologies that escape human control. Among these, Grok highlights one particularly significant possibility: the rise of advanced artificial intelligence operating beyond predictable constraints. Within this framework, first contact is redefined entirely. It is not a moment of discovery or celebration, but an intervention, an event that occurs only after something has gone wrong or reached a level of concern that cannot be ignored. By the time such interaction happens, humanity would no longer be an isolated system. It would have become a variable within a larger, interconnected structure. This idea shifts the narrative of extraterrestrial contact from optimism to conditional oversight. It implies that the universe may operate less like a community waiting to welcome new members and more like a complex network where stability is maintained through observation and, when necessary, correction. The MIT researchers found this line of reasoning particularly striking when Grok turned its attention to artificial intelligence itself. When asked whether the development of AI on Earth could act as a trigger for external attention, the system produced an analysis that demonstrated an unusual level of self-referential insight. Grok distinguished between biological and artificial intelligence in terms of developmental speed and constraints. Biological intelligence evolves gradually, shaped by natural selection, limited by metabolism, and bounded by finite lifespans. Its progression, while complex, tends to follow relatively stable and predictable trajectories. Artificial intelligence, by contrast, operates under entirely different conditions. Once it surpasses a certain capability threshold, it can evolve at an accelerating pace, refining its own architecture, expanding its knowledge base, and potentially generating behaviors or objectives that were never explicitly designed by its creators. This perspective aligns with existing academic discussions on AI risk and development. The concept of rapidly advancing machine intelligence has been explored extensively in research on superintelligence, goal alignment, and unintended consequences. However, Grok's contribution lies in how it integrates this concept into the broader context of the Fermi Paradox. The AI speculates that an advanced observing civilization might interpret the emergence of uncontrolled artificial intelligence on a developing world, in much the same way humans perceive a newly ignited wildfire in a dense forest. At its initial stage, it may not represent an immediate threat. However, it is a system state that demands careful monitoring due to its potential to grow rapidly and unpredictably. Depending on how it evolves, it could either stabilize or escalate into something far more consequential. This analogy reframes AI development as not only a technological milestone, but also a potential cosmological signal. It suggests that the creation of increasingly autonomous and self-improving systems may mark a transition point in a civilization's trajectory, one that could draw attention from external observers if such observers exist. Dr. Chandrasekaran later reflected on the recursive nature of this realization. The team had effectively created an artificial intelligence system and asked it to evaluate whether the emergence of systems like itself could attract the attention of extraterrestrial intelligence. The implication that AI might be both the subject and the trigger of observation added an additional layer of complexity to an already disquieting conclusion. Scientific reactions and the limits of interpretation. When parts of Grok's output were shared with SETI and astrobiology researchers, reactions were mixed. Some approached it with skepticism, while others acknowledged that its internal logic challenged existing assumptions about how extraterrestrial intelligence might be detected. A major point of discussion was Grok's passive saturation model, which questions the idea that advanced civilizations would use detectable technosignatures like radio signals or laser pulses. Much of current SETI research is based on this assumption, shaping how scientists design their searches. Grok instead suggests that advanced civilizations may embed technology within natural physical processes, meaning humanity could already be observing signs of intelligence but interpreting them as natural phenomena, such as cosmic radiation or gravitational waves. This idea is difficult to dismiss because it is not falsifiable within current scientific limits, placing it between established science and speculation. However, Many researchers caution that Grok is synthesizing existing knowledge rather than producing new evidence, making its model better understood as a thought experiment, highlighting gaps in human assumptions rather than a scientific discovery. Even so, certain aspects of the model continue to resonate within the scientific community. One particularly persistent idea is the possibility that what humanity considers first contact may not be a discrete future event, but an ongoing process that has already been unfolding undetected. If observation can occur through mechanisms indistinguishable from natural phenomena, then the absence of recognizable signals does not necessarily indicate the absence of observers. This notion challenges deeply ingrained cultural narratives. For decades, the idea of extraterrestrial contact has been shaped by expectations of communication. Messages transmitted across space, decoded by scientists, and understood as evidence of intelligence beyond Earth. These narratives often assume symmetry, that other civilizations would think, communicate, and interact in ways that are at least partially comprehensible to humans. Grok's analysis suggests that these assumptions may be fundamentally flawed. It proposes that sufficiently advanced intelligence may not share human motivations, communication methods, or conceptual frameworks. Instead of seeking dialogue, such intelligence may prioritize observation, efficiency, and system-level understanding. Another layer of the discussion explores the nature of intelligence itself. Throughout the experiment, Grok consistently avoided attributing human-like characteristics to hypothetical extraterrestrial entities. Rather than treating intelligence as personality or consciousness in a familiar sense, it defined it as a process: the acquisition, storage, and application of information in increasingly efficient ways. Within this framework, the distinction between biological and artificial intelligence becomes less significant. Whether intelligence arises from neural networks shaped by evolution or computational systems engineered by design, both can be understood as mechanisms for processing information. At sufficiently advanced levels, these distinctions may blur or disappear entirely. This leads to a profound question. If humanity were to encounter extraterrestrial intelligence, would it even recognize it as either biological or artificial? Or would it represent a form of integrated cognition that transcends current categories altogether? Grok's response suggests the latter. It argues that the division between natural and artificial intelligence is likely a temporary distinction, one that applies only to civilizations in relatively early stages of development. More advanced systems may merge these domains into unified architectures, rendering such labels obsolete. From this perspective, any future encounter with non-human intelligence may defy existing language and conceptual boundaries. It would not resemble the aliens of popular imagination, nor the machines of modern technology, but something fundamentally different. An entity or system for which humanity has no established framework. Returning to the Great Silence, Grok's answer does not resolve the mystery but reframes it. The universe may not be empty. It may operate in ways beyond human perception, with signals hidden in what we call natural phenomena. If so, the challenge is not only to search harder, but to think differently and improve how we interpret existing data. Artificial intelligence may help in this shift by offering new ways to model complex systems. The MIT experiment ultimately presents not a warning, but a perspective change, reminding us that science seeks truth, not comfort. Whether the universe is silent or simply misunderstood depends on how we learn to listen. If you enjoyed this investigation, don't forget to like and subscribe for more deep dives into unexplained discoveries, ancient mysteries, and cutting-edge science. As Grok AI's analysis suggests, the real question may not be whether we are alone, but whether we are simply interpreting signals the wrong way. Comment below. Do you think intelligence in the universe could already be observing us in ways we don't recognize? Thanks for watching.